Okay, thanks for those kind words, Brent. Let's get started. So I'm sure that everyone here agrees that BPM is great technology and Camunda is a great implementation. And I think everybody here will agree that Camunda Community Day is a fantastic day. Did you know that Gartner recently published an estimate that for an hour of downtime, the average cost to a large organisation is $300,000. And that's just the average cost for bigger organisations that could be much larger. So my name's Rob Parker, I'm from Australia Post, and I'm going to talk to you today about continuous operations excellence. So the reason I talk about continuous operations excellence is we've got a landscape today and it's characterised by patches and upgrades and load spikes, and you might think that continuous operation is not achievable. But the challenge is that our customers are more connected than ever and they're expecting uninterrupted access to services, etc. So using the patterns I'm going to talk through today, I'm hoping that you'll be able to get a much more continuously available shared environment. So using these patterns, you should be able to reduce the duration and the frequency of planned outages. Using the patterns I'll talk through today, you should be able to have a much more sustained operating platform on an optimized deployment. And in addition, you should be able to improve the uptime, throughput and response of your solutions. And some of you might be thinking, this is already solved, we've got stateless nodes, I can throw lots of infrastructure at the problem, I can scale out. Actually, continuous operations is different. There's more to operations than just availability. You don't want to overlook the aspects of an operating environment where you want continuous operation, the ability to concurrently upgrade whilst maintaining the services, maintain liveness, responsiveness of your solution. So many of you will recall that last year I spoke about our use of Camunda, which is, we use it as our service order management platform. So just in very simple terms, we have customer orders coming in from the top. We have what we call our service order manager dispatcher, which routes those orders to be fulfilled. And we call it service order management because these processes take a customer order and they provision a product. So it's not customer order management, we've got the customer order. This is decomposing it into some processes to actually fulfill and provision the product the customer is after. So the way we realise this is for each product we have a fulfillment process and we deploy it as a process application into a shared environment. So we end up with, we might have many small applications, one product per application, one fulfillment process per application, deployed into our shared environment. And last year I spoke about one of the challenges we had, which is how can we upgrade a process version without any downtime, without any outages, etc. And the way we do it is we use a mapping table at the top with our integration layer, and effectively we can deploy a new version of the process application which will generate a new ID in the Camunda system. We can do that before we cut over and go live, so we'll have the old version running and the new version running. And then what we do is in our mapping table we can figure our cutover date and the ID of the new version we've just deployed. So typically this could be at midnight, and effectively once the system rolls over, our integration layer would have been using the old version and now it uses a new version, so that's how we cut over. We found there's a little bit of pain with this, that what we had to do is we are doing a start process instance by ID. And the trouble is you don't know what the ID is until you've deployed your process app. And that's okay in production because you only deploy it once, ideally. But in development and test, you're constantly deploying them, so it's really painful. So as an improvement, one of the things we could consider is there's a new REST API and we can do what I call a double dispatch, which is we could store a process version in our mapping table rather than an ID. And then what we would do is at the appropriate cutover time, we'd make a call into the engine with the version number and it returns the ID, and then we can do a start. So it's double call, but it's only doing on start process instances. So very briefly, that's the architecture I'm going to talk to you today, and that's the architecture I spoke about last year. Burnt, your pop-up has popped up again.
Yeah, I think it's hard to move away.
Which is your mouse?
This one is the mouth. Sorry. Oh, we can wait a second. We can close it once and for all. That.
Thanks.
Almost. That should be. Yeah.
Thank you, sir.
Sorry.
Okay, so what do I mean by continuous operation? I'm sure everybody here understands high availability. It's resistance to unplanned outages. Throw lots of redundant components at your solution and you're done. Or even better, make it somebody else's problem. Use the cloud. Somebody else keeps high availability. So what's continuous operation? I'm talking about this axis here. And it's really what I call resistance to planned outages. So if high availability is your resistance to unplanned outages, continuous operation is your resistance to planned outages. And that's what I want to focus on today, which is continuous operation. And just for some examples, to make it very clear, top right-hand corner there, we have the emergency system. Under 911 in the States, it's 000 in Australia. And from an availability perspective, they can't tolerate any downtime, any outages unplanned. It needs to be available 100% of the time. It needs to be available 5 nines is probably their SLA. And that's availability while it's running. But in addition, they cannot take it offline for maintenance. You can't suddenly shut down your emergency services solution for an hour whilst they do maintenance. It has to be running continuously. So this is what I mean by continuous operation. Airline booking system, very similar. Has to be highly available because if you can't book airline tickets, they're losing money. But at the same time, it's a 24/7 worldwide industry, so they need to be supportive of very high concurrent operation. Corporate email, doesn't really matter if it's offline for an hour, probably don't need it on Sunday. So that's why it's down there. And just to really round this out, stock trading system, it's kind of unusual that it needs to be highly available, probably 5 nines, because when you're doing micro trades and automated trading today, you can't tolerate any downtime. But it doesn't need to be continuously operating because the stock market is only open 10 till 4 Monday to Friday. So you've got overnight and you've got weekends to take it offline. So that's the difference, continuous operation and availability. So what's the problem? If there's one certainty in IT, it's that things change. And in this case, I've got a process engine version change. Reason why, your support window is only a few years, so ultimately your version you're running on is going to fall off the support wagon. You might have supporting infrastructure changes, a database, etc., which you have to upgrade. And that might be incompatible with the current version of your engine. So the challenge is we need to be able to upgrade the core version of the engine. So what's some of the approaches? This one is what we call the Big Bang upgrade. Most organisations will face this, and we're facing this ourselves in our current deployment platform. Basically, it's an upgrade in place. It's pretty simple. You shut down your servers, provided you can. You run the migration scripts, you restart your servers, you've done an upgrade. So the strength of this approach is it's consistent with the approach recommended by Camunda. They provide the scripts, etc. It's simple from an implementation perspective. There's no changes required to external systems because you're not changing IP addresses or changing domain names, etc. In our case, there's no changes to our TIDCO BusinessWorks integration layer because it's effectively talking to the same implementation. We have JMSQ listeners, which is what we use for accepting events from external systems, and they will then call the correlation API down in the engine, so we don't need to change those. And administrators can use the same SOM dashboard, users can use the same tasks, etc. Nothing much changes. So that's the Big Bang upgrade. And at the end of it, the outcome is you've basically retired the old version and you're on the new version. But what's the catch? There's potentially a large outage. If you're taking it offline and upgrading in place, you've got an outage, so you don't necessarily have continuous operation. For us, we can do this because our middleware tier effectively isolates us from any temporal coupling. So in other words, our TIPCO integration is always a store and forward pattern, which means we can actually take the engine offline, we could do an upgrade in place, and the clients would be none the wiser. So temporal decoupling is your friend. But what are the other challenges which can exist? Well, if you've got projects in flight and you've got new business processes, which version do they target to go live on? For example, if a project's running late, that's okay. But if you're running late and they've already targeted the version for your upgrade, then suddenly you might block the project. So you might have a timing dependency on projects. And what if you have a problem during the upgrade? In the shared engine environment, suddenly it's everybody's problem. Some other characteristics of this is, if you're doing this big bang upgrade, you may have a large regression test load on your testers because suddenly you're testing lots of apps in a very short window of time. So you actually might run out of testing capacity. As a consequence of that, you might also lock in the business because your testing cycle is so long and the business wants to introduce change, so you get this lock-in. So big bang, very easy, but it has some challenges with continuous operation. But wait, there's more. What else makes this difficult? Not all of our process applications and the dependencies can be upgraded at the same time. We have different business units which might have different priorities. We have a seasonal low in one product which may correspond to a seasonal high in another product. So it can be hard to find a time when your system usage is at a low and you can do these kind of updates. We have time of day usage profiles which might have opposing highs and lows. We have lots of customer interactive orders which come in during the day, and overnight we have more batch-oriented orders, so there's not the daily or nightly peak. And as I said, we might have insufficient regression sources, testing sources, resources to get through it before something changes. So we can kind of get this lock-in. So here's an alternate strategy which we're contemplating after our big bang, and it's what I call the rolling strategy. So effectively what we would do is as there is a new Camunda version released, we can stand up a new instance and we can start to either migrate apps across one at a time. If we've got new applications, they could go straight into the new version, etc. And so you can kind of see how we can start to roll through much more smaller changes. So one of the challenges with this is we can effectively migrate an existing app and we'll have two versions in production at the same time. And that's okay with our dispatcher. And this is where it comes into its own, because we've already got a cutover date in there which will map to a process version. And so what we would plan to do with this architecture is we introduce another attribute which is a location. So now when we deploy a new process version into maybe an upgraded engine version, we can configure our mapping table with, at this point in time, I actually want you to cut over to this version, and by the way, it's in this location. So we can start to roll process versions through. We have continuous uptime. Our dispatcher is able to dispatch across these things. So the strength is that you can start to migrate your business process applications one at a time, and you can do it at a point where it's most suitable for that app. So you're not now locked in by the business, you're not locked in by seasonal peaks, you're not locked in by any other project implications. And if we take this to its conclusion, eventually we might have multiple instances in production, multiple versions, but eventually you would have migrated all your process applications off your most legacy version and you can actually retire that. So what's the challenge with this? Well, it splits the process history into multiple databases, and that can make your reporting more complex, so that's a bit of a challenge. Whilst we could have processes to export the history into a common data warehouse, etc., you could run into a challenge where the history schema has changed with a major release of the Camunda engine. The other challenge is administrators will have to deal with multiple cockpits, but they're used to that, so they tend to cycle through screens. But your users may have a challenge that they might be using a task list which has a certain URL for the old process version, but it's got a different URL for the new process version. And if you've deployed your engine such that you've got new processes running in the new one and you've still got some old ones which are completing the old version, suddenly your users have two task lists which you now have to deal with. So if you've only got a few processes and they don't take very long and they complete in a day, your users might be able to deal with that. But if you've got really long-lived processes, you might want to think about migrating your processes. The other challenge here is event correlation becomes interesting, because when an event comes in, where do I dispatch it to? Now we could put the global process map connected up to the queues and use that to dispatch, but that means you must be able to, from the event, be able to interpret which version it goes to. So an alternate strategy is, as the event comes in, try and correlate it with the latest engine, and if it doesn't correlate there, fall back to the previous version and keep falling back, and if it doesn't correlate, then something's gone wrong and you don't have a process version or process instance to correlate to. And over time, by targeting the most recent deployment, effectively all your new instances will be on that, so you won't be calling across multiple nodes. Okay, so this is another strategy which is kind of similar, and we call it the engine-based upgrade strategy. And the approach here is, rather than have a shared engine with multiple apps, maybe our granularity of sharing should be a tenant. And actually what we do is we can migrate tenants across versions. So it's very similar to the rolling upgrade strategy, but the granularity is now a tenant and we have one process app per tenant. So it's a little bit of a hybrid of the two. It's a big bang upgrade relative to the tenant, because you're taking a tenant on one version and you're upgrading it to a completely different version. But it's got the characteristics of the rolling upgrade, because rather than taking the entire engine, you're now just taking a tenant within the engine. So some of the issues with this is there's overhead with running multiple tenants on the same hardware. You've got duplicate job executors, etc. So you have to be very careful with your resources. But one of the really great features of this is we can, with DNS mapping, make it location transparent. So if we shift an engine from one location to the next, our users don't have to get given a new URL. We can effectively have a URL per process application, and if we move it around with DNS mapping, the user is none the wiser. So that's kind of a good experience. So there's some strategies to upgrade. What's the next challenge? Apart from continuous operation, we need throughput. And in a shared engine, you may have competing resource requirements. You can have I/O-bound processes and CPU-bound processes, and we want to operate as efficiently as possible. So what do? Measure, test, tune, repeat. So we did some testing ourselves, and we used a single AWS RDS instance with 4 CPUs, because we didn't want the DB to be a bottleneck. And we wanted to explore the characteristics of the job executor. Now, when we were doing this, we were doing it on version 7.2 of the engine, so things have actually moved on quite a bit. Thanks to Feldman's work, wherever he is, and I'll come back to that. And so what we did is we put some load through, we loaded up we stopped the job executors, we loaded up the system with about 6,000 process instances, and we restarted the job executor. And here's our process, which is just a fairly basic process. Very similar characteristics to our fulfillment processes. They're typically service tasks because they're orchestrating across systems to provision stuff. Lots of service calls, which are generally remote procedure calls. And in the testing we did, what I did was configured one version where the time to make a remote procedure call was anywhere from 100 up to 2,000 milliseconds. So that's 100 milliseconds up to 2 seconds. And a different version where we went from 50 to 200 milliseconds, so much more reasonable. But some of our solutions do have locking or remote procedure calls which can take up to 2 seconds. And what did we find? Well, this is a normalized plot of the average processing time per threads in the thread pool. And this is a Tomcat deployment. So the default thread pool size is 10. And what we found in our circumstance is if we increase that to 20 or even 30 threads, we tended to double the throughput of the solution. And this makes sense because if I've got a lot of threads in the thread pool and they're spending up to 2 seconds in blocked I/O waiting for remote procedure call, I've got a lot of threads not doing much activity. Whereas the job executor, it can pull jobs out of the database much, much faster. So it makes sense in this kind of landscape that your bottleneck will be the thread pool size and you need lots of threads. And in fact, in this environment, we could keep going up to 90 threads and getting marginal improvement. But at around about 90 threads, I think that's where the resources and contention on the Tomcat machine starts to become the next bottleneck. So 30 was a good sweet spot. The other interesting characteristic is whilst one set was, say, 100 to 200 millisecond latency and the other run was up to 2000 milliseconds latency, the shape of the graph is very similar. So another thing we did was we wanted to ensure that it was actually the thread pool which was the bottleneck. So then we set up a cluster. So 2 nodes, exactly the same configuration, etc., etc. And what we found there was throughput doubled. Now that makes sense because if your job executor is still not the bottleneck and your database is still not the bottleneck, and your bottleneck is the thread pools at about 90, then if I can double that, I would get double the throughput because I've now removed one of the bottlenecks. So I guess the lesson here is tune your job executor, tune your thread pool. Your results may be different from ours. It depends on your environment. I'd suggest if you've got a lot of blocking I/O, more threads is good. If you've got very CPU intensive characteristics, less threads is good. Okay, liveness. What's the problem here? It speaks for itself. You can have lots of activities which are not that value adding and they can be blocking the more expensive or the more time critical ones. So in our environment, we have some, because we're in a shared environment, we've got some processes which are more time sensitive than others. And for example, we've got one product and its provisioning process can take a couple of days because there's some physical activities to perform. Whereas in another product, there's an expectation from the customer that it will be complete in terms of its provisioning within about 15 minutes. So under normal load, this wouldn't be a problem to us. We're fairly confident we can get through the throughput. But one of the challenges that we have is one of the products, and particularly the one with the 2-day kind of fulfillment processing time, we renew all of those products at the same time annually. So it means in about a 2-week period, we will go through 1 million renewals. And our concern there is we can flood the system with so many fulfillment processes that the job executives are really busy churning through those processes and the time critical ones are kind of lost in the chute, so to speak. So one of the thoughts we had with this architecture was to introduce what I call a liveness node. So we've got our standard service order management deployment, but I've got this little node called Camunda Live. And the intent there is whilst the main cluster is a homogeneous cluster, this live node is a heterogeneous one. It only has the one app on it. So therefore we configure the job executor there with the to be heterogeneous. You'll notice that it doesn't participate in any of the interactive or the integration landscape. It's just there as a job executor. So the intent there is, in terms of liveness, if suddenly one of these time-sensitive orders comes through, this particular node won't be doing anything. It might be polling the job table, but it's not going to be picking up all those sheet kind of processes. This is for the Lamborghini. A couple of challenges here, which is live lock can become a concern, because if you need to do this at scale with multiple apps, then suddenly you might have too many nodes hitting the database, and with the job executors or the old job executor, you could start to get live lock where they start falling over each other. Fortunately, this is on our plan B, and we haven't deployed it to production because with the new job executor and job prioritization, that's a much better solution than this solution. So this is our plan B in case we needed it for the future, but I don't think we'll actually deploy on this. But it does leave some interesting questions on deployment architecture, which is, even with a new job executor, should we consider separating out nodes which participate in the interactive and the event correlation versus nodes which do nothing more than do the job executor type work? In addition, if I did have that two-tier architecture with the job executors, is there any value in configuring one job executor to be priority-based and another one to be order-based, such that they don't conflict so much in terms of their database contention? But that's kind of like an out there question for the future, and I'm looking forward to getting the 7.4 release. So, it's been my pleasure to share our operational experience with you guys. In summary, don't overlook the operational aspects of your solutions. Plan for change, plan for resource upgrade, plan for upgrades, plan for resources. Why? Because customers are more connected. The world is more connected. Web scale is the new norm. Scheduled maintenance may become a luxury. What do? Ensure your architectures, deployments, and operations processes can meet the new norm. Loose coupling is your friend. Aim to reduce coupling, particularly temporal coupling, as much as possible, ideally 0. Measure and tune, and plan. Expect the unexpected.